Welcome to our video on linear transformations and matrix algebra. Today, we'll learn about linear transformations, their matrix representations, basic matrix operations, and how to find the inverse of a matrix. Let's start by understanding what a linear transformation is. A function t from Rn to Rm is called a linear transformation if it satisfies two key properties. First, additivity. T of u plus v equals t of u plus t of v. Second, homogeneity. T of c times u equals c times t of u for any scalar c. In simple terms, a linear transformation preserves vector addition and scalar multiplication. Let's look at an example of a linear transformation t from R. 2 to R, 2 defined as t of x, y equals the ordered pair, 2x plus y, and x minus 3y. Let's verify that this is indeed a linear transformation by checking the two properties. First, let's confirm additivity using two generic vectors, u and v in R2. If u equals a, b, and v equals c, d, then u plus v equals a plus c, b plus d. Now, t of u plus v equals t of a plus c, b plus d, which equals 2 times a plus c plus b plus d, and a plus c minus 3 times b plus d. Using the distributive property, this equals 2a plus 2c plus b plus d, and a plus c minus 3b minus 3d. Rearranging, we get 2a plus b plus 2c plus d, and a minus 3b plus c minus 3d. Notice that this is exactly t of u plus t of v, confirming additivity. Similarly, we can verify the homogeneity property. Now, let's learn how to represent a linear transformation using a matrix. Any linear transformation t from Rn to Rm can be represented by multiplication with a unique m by n matrix A. So, t of x equals a times x. To find this matrix A, we apply t to each standard basis vector, and the results become the columns of A. In R2, the standard basis vectors are e1 equals 1, 0, and e2 equals 0, 1. Let's apply our transformation t to these basis vectors. For e1, which is 1, 0, we get t of e1 equals 2 times 1 plus 0, and 1 minus 3 times 0, which simplifies to 2, 1. For e2, which is 0, 1, we get t of e2 equals 2 times 0 plus 1, and 0 minus 3 times 1, which simplifies to 1, negative 3. Now, we can form the matrix A. The first column is t of e1, which is 2, 1. The second column is t of e2, which is 1, negative 3. Therefore, the matrix representation of our transformation t is this 2 by 2 matrix. Let's visualize how this matrix transformation affects the entire plane. Here we have our original coordinate system with the standard basis vectors e1 and e2. When we apply the transformation t, each point in the plane gets mapped to a new location. Notice how the basis vectors e1 and e2 are transformed to the columns of our matrix A. This is why the columns of the matrix represent the transformation. They tell us where the basis vectors go. And by linearity, this determines where every other vector goes. Now, let's discuss basic matrix operations. Given two matrices A and B of compatible sizes, we can perform several operations. First, matrix addition. When matrices have the same dimensions, we can add them element by element. For example, if A equals the matrix we found earlier, and B is this matrix, then A plus B is calculated by adding corresponding elements. Second, scalar multiplication. We can multiply a matrix by a scalar by multiplying each element of the matrix by that scalar. Third, matrix multiplication. To multiply matrices, the number of columns in the first matrix must equal the number of rows in the second. For our 2 by 2 matrices A and B, the product A times B is calculated using the following rule. The ij entry of a times B equals the dot product of the ith row of A and the jth column of B. Let's compute a times B for our example. For the 1 entry, we take the dot product of the first row of A, which is 2, 1, and the first column of B, which is 0, 5. This gives us 2 times 0 plus 1 times 5, which equals 5. For the 1, 2 entry, we take the dot product of the first row of A and the second column of B. This gives us 2 times 4 plus 1 times negative 1, which equals 7. Similarly, for the 2, 1 entry, we get 1 times 0 plus negative 3 times 5, which equals negative 15. And for the 2, 2 entry, we get 1 times 4 plus negative 3 times negative 1, which equals 7. Therefore, a times B equals this matrix. Finally, the transpose of a matrix, A, denoted a transpose, is obtained by flipping A over its main diagonal, effectively turning rows into columns and columns into rows. Now, let's discuss the inverse of a matrix. A square matrix, A, is invertible if there exists a matrix A inverse such that a times A inverse equals A inverse times A equals the identity matrix, I. For a 2 by 2 matrix, we can directly compute the inverse using a formula, but for larger matrices, we typically use methods like Gauss-Jordan elimination. A matrix is invertible if and only if its determinant is not 0. Let's find the inverse of our matrix, A. First, we calculate the determinant of A, which is 2 times negative 3 minus 1 times 1, which equals negative 7. Since the determinant is not 0, A is invertible. For a 2 by 2 matrix, we can use the formula. The inverse of A equals 1 over the determinant of A times a matrix, where we swap the diagonal elements, negate the off-diagonal elements, and flip the signs. Applying this to our matrix, A inverse equals 1 over negative 7 times negative 3, negative 1, 2, which equals 3/7, 1/7, 1/7, negative 2/7. To verify that this is indeed the inverse, let's multiply A times A inverse. When we multiply these matrices, we should get the identity matrix. Indeed, A times A inverse equals 1, 0, 0, 1, which is the identity matrix I. This confirms that we've correctly found the inverse of A. In conclusion, we've covered 4 important topics in linear algebra. First, we learned that a linear transformation preserves vector addition and scalar multiplication. Second, we saw how to represent a linear transformation as a matrix by finding where the standard basis vectors go. Third, we explored basic matrix operations: addition, scalar multiplication, matrix multiplication, and transpose. Finally, we learned how to find and verify the inverse of a matrix. These concepts are fundamental to understanding linear algebra and have applications in countless fields, from computer graphics and machine learning to physics and engineering. Thank you for watching.